to Okay, cool. So I guess I'm pleased to introduce my friend from grad school, Andrew Graus, who's currently he got his PhD at UC Irvine and is now a postdoc at the University of Texas Austin. He's going to be telling us today about the destruction of satellites around the Milky Way. So please, Andrew, start.
All right, great. And thanks, Ryan, for that introduction. It's good to virtually be here, and I appreciate the invite. I'm going to talk a little bit about sort of the current state of simulations of the Milky Way and what we can sort of learn about the satellite galaxies that are destroyed. And if anybody has any questions during the talk, please go ahead and raise your hand, and I'll be sure to call on you. So I'll start with a little bit of an introduction. So I'm going to start by sort of talking about the current state of simulating the Milky Way, and specifically focusing in on what we can learn about simulating subhalo disruption, basically as galaxies that orbit and then get destroyed. And then I'm going to have go into a focus on individual subhalos and what happens to them as they orbit around the Milky Way. And then I'm going to talk about applications of this and why this is important and interesting. And I'm going to focus on 3 different areas. One is for gravitational lensing studies. Another is for looking at gaps in globular cluster stellar streams. And then finally, I'll talk a little bit about insights we can gain into high redshift star formation using things that we learn from subhalo disruption. So to start with sort of the current state of the field, over the past, I would say 5 years or so, we've started to get like really great simulations, hydrodynamic simulations of the Milky Way. So for my part, I am part of the FIRE collaboration, which uses the code Gizmo, which is a fully hydrodynamic code with modeling stellar feedback and star formation physics. And one of the remarkable things about this sort of new wave of simulations is that we're able to sort of reproduce galaxies like the Milky Way with like really shocking accuracy. So this is one of the simulations, M12I, which is a Milky Way size halo. And inside of this halo, it forms a spiral galaxy. And so you can see on the left there, pretty clear dust lanes and spiral arms. And then on the right, you can see an edge-on view where you can see just how thin that this disk has. So we're able to sort of reproduce sort of basic properties of the Milky Way in simulations, which is pretty exciting. And for us, one of the things that we've noticed as we've sort of began running these simulations is there's actually a difference in the subhalo populations between these sort of fully hydrodynamic simulations with star formation and feedback physics, and then if you were just to run a cosmological simulation with dark matter only, not modeling the actual baryonic physics. And it's in typically in the central regions, we see a depletion in the number of subhalos that are close to the Milky Way. So we have here is a plot from a study by Shea, Garrison, Kimmel, where he took one of these FIRE Milky Way-like galaxies and then simulated the same thing in dark matter only. And you can see kind of the dark matter density plot of these 2 halos of Milky Way on top. And then in the bottom, there's kind of the zoom in on the inner 50 kiloparsecs or so around these 2 halos. And what you can see on the right or in the middle of the figure is that there's a very clear depletion in the number of subhalos in the hydrodynamic simulation as opposed to the dark matter only simulation. So something about these hydrodynamic simulations is actually aiding in the disruption of subhalos very close to the galaxy itself. So to put a little bit of numbers on this is another plot from Garrison Kimmel et al. 2018, where we looked at, this is just the subhalo mass functions. So this is the number of subhalos as a function of mass, cumulative, reverse cumulative going down. And what's plotted here is dark matter only as those sort of thin dashed lines, which you can see is very high up. It's kind of, you get the most subhalos in these kinds of simulations. There's also the FIRE simulations, the full hydrodynamic simulations. And to sort of put a test and to put in a sort of test of what's actually causing this additional disruption, Shea put in a sort of galaxy potential by hand. So basically took the dark matter only simulation and just put a Miyamoto Nagai potential in the center to sort of mock the effect of a disk growing on the subhalo population. And what you can see is that that sort of thicker dashed line, which is the dark matter only plus disk simulations, actually reproduce this depletion in subhalos, about a factor of 2 depletion of subhalos, pretty accurately. And so, so if we look at this sort of picture of the subhalos themselves again, we can add on this sort of third column, which is this dark matter only plus disk simulation. And now when you sort of look down at the inner 50 kiloparsecs, you can see that there's a similar depletion close into the actual galaxy of the Milky Way. That is, once again, not seen in dark matter only simulation. So something about having this additional potential of the Milky Way is aiding in disrupting these subhalos. And so what we did afterwards was a graduate student at UC Irvine, Tyler Kelly. He ran a suite of 12 of these dark matter only plus disk simulations. Number one, because they're much cheaper than a full hydrodynamic simulation. And also because we want to sort of look very specifically on the sort of destruction that comes from the disk specifically. So we don't want to sort of have to deal with the effect of feedback or other things like that. So he ran a suite of 12 of these systems. And he did a little bit more accurate accounting for the galactic potential. So in the beginning, we just sort of put in a disk potential and just sort of let it go. But this one, Tyler actually modeled it as a sort of a triple disk to model both the stellar disk, the gas disk, and the bulge. And then calibrated the masses of those using abundance matching, and then got the sort of scale radii from the disk from observational samples such as candles. And so on the left here, you sort of see the mass of the different components of one of the disks in one of these simulations as a function of time. So we sort of plop in the disk potential at around redshift 3, and then let it grow both in mass and sort of scale radii and scale height according to observational studies. And you can see how that mass grows over time to the present day. So kind of a result of these simulations was we were able to sort of recover this basically factor of 2 disruption of subhalos at the virial radius that was seen in the sort of test case by Shea, Garrett, and Kimmel. We were able to sort of reproduce that. And so now we have a much larger sample. So what's shown here on the left is the V peak function. So instead of looking at mass, I'm looking at the maximum circular velocity of the halo, and then looking at what the peak of that circular velocity was over all time. So we're looking at sort of the most massive these subhalos ever were, and then looking at that basically a mass function of that. And so you can see that the median, those 2 thick lines, are the median of the distributions, and you can see that there's a factor of 2 decrease there. But to look at this in a little bit more depth, we can do something like plotting the radial distribution of subhalos. So we're now plotting everything with a V peak greater than 6 kilometers per second. And we're plotting just the number of subhalos as a function of radius. And this is cumulative going outward. And what you can see between the dark matter only simulations and these ones with the disk potential is that while there's about a factor of 2 to 4 decrease at 100 kiloparsecs, it gets much, much more severe as you get very close to the halo. And by the time, it's about a factor of 5 at about 100 kiloparsecs. But by the time you get to about 20 kiloparsecs, it's more like a factor of 10 decrease in the number of subhalos. And furthermore, there's a sort of innermost radius for subhalos that's very different between the dark matter only simulations and the disk simulations, where you wouldn't necessarily expect to find many subhalos at all within about 20 kiloparsecs. Now you might ask yourself, are we confident at all that this is actually happening? Or is this maybe some sort of simulation artifact? And one thing that sort of points towards this maybe being true is we can look at the pericenter distributions of these simulations. And so what's plotted here from one of Tyler's works is the pericenter, basically the histogram of the pericenter distributions for the subhalos in these two sets of simulations, with the dark matter only simulations and that dashed line with that gray distribution. And what you can see there is that the pericenter distribution kind of increases without limit, basically going down to the center. So subhalos are able to get sort of arbitrarily close to the Milky Way itself and still have lived to the present day, more or less. Whereas in these disk simulations, there's a peak. So that solid line, the black solid line, is the pericenter distributions from our disk simulations. And like we were seeing before, you don't really see subhalos within about 20 kiloparsecs. And any subhalo that has a orbit that takes it within 20 kiloparsecs is disrupted on a very short timescale, as we'll see in a little bit. So we can actually look at the observational counterpart to that, which is basically with Gaia, we've been able to get proper motions and accurate distances to a lot of the dwarf satellites of the Milky Way. And what you can see is that the pericenter distribution, which is shown in red, derived from those observational, those observations from Gaia, matches pretty well to this to these disk simulations, where you see a very clear peak at around 20 kiloparsecs. Now, of course, there's caveats to the observational measurement. There are, of course, errors in the Gaia proper motions and distances. And then there are also, you also have to, in order to get the pericenters from their present day positions and motions, you have to sort of assume a gravitational potential and then run that picture back. So this is particularly using a light Milky Way model. And so if you change it to a heavier Milky Way model, it doesn't change it all that much. But there are also assumptions in these models that you use to sort of run back and get the pericenter distributions. But this is at least telling us the fact that we're seeing a peak in the pericenter distribution from the observed galaxies and in our disk simulations is maybe pointing towards the fact that this is actually real subhalo disruption and not some sort of artifact, simulation artifact. So now I'm going to take a closer look at subhalo disruption, and this is work that that has been led by a grad student I've been working with at UT Austin, Hyun-Soo Kong, and so he's specifically been looking at these simulations, these PLVIS simulations from Tyler Kelly, and looking very specifically at individual subhalos and tracking them over time and seeing what's happening with them as they get disrupted. So I'm going to give you two cases here. I'm going to give you a weak case and a strong case. And so this is the weak case. So what you can see in the sort of top left is a projected map of what the orbit of this halo looks like, both in its disk simulation and then the corresponding dark matter only simulation. So these are the same simulations, just one has a disk potential in it. So we're able to identify the same subhalo in both cases and see how things change. And so what you can see is that sort of black star is the beginning, basically when it falls into the virial radius of the Milky Way. And then the sort of dashed line is the orbit that the dark matter only simulation takes, and the solid line is the orbit that the disk takes. And what you can see is that, at the very beginning, they kind of track each other quite well. And then quite quickly, after a couple gigayears or roughly one orbit, they start to deviate from one another in a rough way. And so in the bottom right, you can see that in greater detail with basically the halo distance as a function of time to the present day. And so you can see that there's kind of a small deviation in the orbits because of the influence of this disk. So what's actually happening to the subhalo as it's orbiting? Well, on the left here, we can look at the actual properties of the subhalo itself. One thing that we did was look at the density as a function of radius. So this is just a density profile, which is shown on the left, with the dashed lines from the dark matter only simulation and the solid lines from the disk, and then colored by the time, basically. And then on the right, you see the circular velocity profile. So this is just the rotation curve, roughly, of this halo as a function of radius. And once again, same color scheme, same line styles. And what you can see is for this case, what happens to the subhalo is not much. It sort of gets a little bit of its mass stripped, but this mass stripping is pretty similar between both the dark matter only and the disk simulation. There's not really too much difference. And so this is why I'm sort of calling this the quote unquote weak case. Now I'm going to look at a corresponding strong case. So this is a case where we found a subhalo whose orbit changes very differently, and it sort of ends up in a much different state between the dark matter only and the disk simulations. So it's again in the top left, you can see sort of the orbit diagram of this object, and then in the bottom right, you can see it's the distance over time, the orbit in another way. And one interesting thing about this is there's, this thing came in with a much smaller impact parameter, so its orbit is tighter. And so the disk potential has a much greater influence on the orbit of this subhalo. And what you can see is after it's been orbiting for about 4 or 5 gig years, the orbit starts to deviate a lot. And in fact, something interesting happens in this case for the dark matter only simulation case. The orbit almost circularizes. It becomes kind of circular and then kind of stays at the same radius as a function of time near the end. Whereas because of the influence of the disk potential, the subhalo in this disk simulation case continues on this sort of plunging orbit that takes it very close, and it has a few orbits where it goes within about 20 kiloparsecs. And so now if we look at the density profile and the circular velocity profile, you can see that there's a very clear difference where in the case of the dark matter only simulation, those dashed lines, the stripping is about what we saw in the weak case, where it's stripped a little bit over successive orbits, but doesn't really change all that much. But if you look at the corresponding halo in the disk simulation, it undergoes very severe disruption. And so you can kind of see that its density decreases by a factor of 100 over these orbits, and its circular velocity profile, it's basically right at the point at the end where it's basically about to be disrupted, and we've sort of completely lost it. So of course, I'm a galaxy formation theorist, so I would be remiss to not have a movie in my presentation. So this is basically a movie of a subhalo being disrupted that Hansu made. And so this is basically going to be focused on the subhalo itself in one of these disk simulations as it orbits through successive orbits. And you can see the orbit on the bottom left there, and you'll sort of see the star that represents the halo move over time. And so what's going on here is, and so as we sort of run this movie, as it gets towards pericenter, what you'll see is that particles, basically dark matter particles, are being thrown off in sort of waves, right? And so and once we get to sort of very late times, you'll see a sort of coherent stream of dark matter that is basically sort of the remnants of the rest of the subhalo that's been disrupted over time as it kind of loops and orbits over time. Oh, whoops. Let's show that again. And one interesting thing that you'll see is that, this throwing off of particles happens right after it reaches pericenter. And so what's happening here is you have some, basically what's happening is as you get closer and closer to the center of the galaxy, the tidal radius, basically the radius where the gravitational force between, or the external gravitational forces and the gravitational force between the subhalo itself is equal. So as you kind of go closer and closer to pericenter, that tidal radius shrinks and shrinks, and then eventually kind of cuts into the subhalo itself. And then once you go out and start heading toward apocenter, there's your tidal radius increases, but it's actually not able to recapture all of those dark matter particles. They're sort of lost forever. And so that creates a stream, and that's what sort of disrupts this object over time. So to put a little bit of numbers on it, so what I have here is this circular velocity profiles that I've shown you before. But instead, what we've done is we've mapped out just a few of the orbits as it goes around the halo. And you can see where they are in the orbit on the right-hand side of the orbit diagram there. And so what we've done is there are different stars as it goes through successive paracenter passages. And then on the left-hand side, we've numbered basically where in its orbit it is, where 0 is closest to paracenter, and then 1, 2, and 3 are going further out toward apocenter. And what happens through successive orbits, what you can see is that it starts at that 0 position, basically right at paracenter, and where it actually is kind of compacted a little bit. It's actually constricted a little bit. And then once you kind of leave paracenter, you're sort of losing those particles. So you end up the subhalo both expands. So the sort of peak of this Vmax function goes outward. And then also because you're losing mass, the maximum circular velocity falls as well. And so what you see is like over these successive orbits, it's losing a bunch of mass. But it's actually also, once it reaches paracenter, kind of constricting to the point where it actually reaches a higher Vmax than it did during the previous orbit's apocenter, which I think is pretty interesting. So let's look, now that we've looked at these subhalos individually, now we can sort of think about them as a population. So these are the subhalos from one of the simulations in our suite. These are all the subhalos. And specifically, we've marked the dark matter only objects with cyan, and the magenta objects are from the disk simulation. And in addition, we have these open squares, which is basically objects that are destroyed in the disk simulation. So you can see their corresponding subhalos from the dark matter only simulation in cyan up top, and then kind of down at the bottom in magenta is the subhalo, basically what its Vmax versus Vmax when it fell in. Basically, you can think about how much it's stripped right before we lose track of it. So at redshift 0, those sort of pink objects at the bottom, they don't exist in our halo catalogs, but that's kind of where they are right before we lose track of them. And what's interesting is you can see that in these two plots, the x-axis on the left is number of paracentric passages. And so what we see is that if you kind of match the sort of open squares from the dark matter only and then the disk simulations in general seem to be undergoing more paracentric passages. So this is kind of evidence that as a population, we're seeing these subhalos getting their orbits changed by the presence of the disk. And so these additional paracentric passages are potentially what's aiding in disrupting these subhalos. Now, another thing we can look at is just the paracenter distributions of these two sets of subhalos. Unsurprisingly, the things that are disrupted, those sort of objects down at the bottom below that dashed line, they tend to have much smaller paracenters. And then in addition, on the right, you sort of see a cumulative distribution of the paracenter distributions. And what you can see is that as a population, the paracenter distribution for the disk simulation is very slightly skewed inward. So these things tend to be drawn, subhalos tend to be drawn statistically into very slightly different orbits where more of them have closer paracentric passages, which sort of is aiding in their disruption. All right, so I've talked a bunch about what's actually going on, what we see in our simulations, and with this sort of subhalo disruption. And so now I'm going to talk about reasons why this is important, what this could sort of impact. And the first thing I'm going to talk about is detection of dark halos with gravitational lensing. So, one of the interesting things that, we've seen over the past decade or so is people like Simona Vighetti using, observations of lensed galaxies. So this is one of the SLAC sample galaxies where they see, a very clear Einstein ring, and then they model this with a sort of smooth halo, and then they sort of check whether or not there's potentially a an additional perturbation to their lensing model that could be an undetected subhalo. And so this is a paper where they were reporting a detection. So you can see sort of the data of this sort of lensing arc on the left here. And then on the right, you see that they're sort of, after their analysis, that sort of red point is where they believe that they found a subhalo of this object. Now, in this case, we're talking for gravitational lensing, we're talking about galaxies that are much, much larger than the Milky Way. So these are elliptical galaxies, so they're about 10 to the 13 halo masses rather than 10 to the 12. But the same principle should apply. These things have subhalos. They also have an actual, baryonic potential from the disk, and so you would expect there to be similar subhalo disruption. And this was verified by a few different papers, including ones by myself and Yulia Despali, but I kind of want to focus in on a more recent paper by Alex Lazar, a graduate student at UC Irvine, where he looked at the illustrious TNG simulation, which is a full box hydrodynamics simulation of basically about 100 megaparsec box. And so they ran two versions of this simulation, one with full hydrodynamics and one in dark matter only. And so what Alex did was look for galaxies that could be gravitational lenses, basically 10 to the 13 halos, and sort of counted up subhalos basically along sight lines to them. Because of course, in gravitational lensing, it doesn't really matter where the subhalos are. It just matters, it's just sensitive to the mass along the line of sight. And so, kind of up in the top left is a schematic diagram of what this would look like. So, pink is the actual subhalo, or the halo of the elliptical galaxy, the lensing galaxy, and then all the pink dots inside of that are its subhalos. And then, but there's also going to be subhalos along the line of sight. And so he's counting up all of these subhalos in this cylinder and sort of making projections for how many subhalos we would expect to encounter along one sightline, one of these galaxies. And so one thing about this cartoon is it's actually over-exaggerating the radius of the cylinders that they use. The actual cylinder that they used is about it's the size of the Einstein radius, which is about 10 kiloparsecs for these types of galaxies. And so you can think of it in reality, the cylinder is a much thinner tube kind of going straight through the elliptical galaxy. And then in the bottom right, what they showed is basically the average number of subhalos you would encounter as a function of this sort of cylinder length. And so what you can see is that, in general, one would expect to encounter much less than one subhalo along one of these lines of sight, basically around, one subhalo every 10 sight lines or so. But what's interesting is the pretty big difference between Illustris, the full hydrodynamics simulation in magenta, and then Illustris, the dark matter only version in cyan. And so similar to what we see in the Milky Ways, you see a similar subhalo disruption. And because the density of subhalos is so much larger, close to a large object, when you look sort of cumulatively, as you're going out to even 100 megaparsecs, that difference between the dark matter only and full hydrodynamics simulation gets kind of baked in. So even at the sort of edges of the box, if you take a cylinder and take it out to the edge of the box, there's still a huge difference in the number of subhalos, because the subhalos that you would see along the line of sight outside the Virial radius are kind of subdominant to the subhalos that we'll see close in to one of these halos. So this is important for subhalo lensing because it gives us an important comparison about what to expect. So if you're assuming, subhalo statistics based on dark matter only simulations, you're going to expect to see many more subhalos in the subhalo lensing technique than we would expect now that we know more about substructure lensing. So in addition to this, another area that I think is very interesting where this factors in is in globular cluster stream gaps. So, similarly to how these galaxies are disrupted, there are also a bunch of globular clusters that are flying around in the stellar halo. And these will also get disrupted over time and form these very long, thin, cold stellar streams. And these are actually really interesting potential probes of dark matter, because what can happen is something can pass by this dynamically cold stellar stream and heat it up and create weird features in these streams. So in this case, this is the GD1 stream, which is one of the closest of these globular cluster streams to us. And they've actually identified this gap, which you can see, sort of at the center here, this sort of, they call it a spur, this kind of lightly colored gray, feature up here. And they think that this is created by something passing by this globular cluster stream and perturbing it in some way. And so Anna Banaka did a bunch of theoretical models of, basically throwing a bunch of objects of different masses and sizes at a globular cluster-like stream to sort of see if they can recover this feature. And so what they reached at the end of the day was that this object must have had a mass and a size in this sort of gray shaded region over here. And then on top of it, they plotted a bunch of different types of objects, other globular clusters, dwarf galaxies, molecular clouds, and then as a distribution, sort of lambda CDM subhalos here. As you can see, maybe just barely, it would have to be a very statistically outlier compact subhalo, but it's theoretically a dark matter subhalo. But it could also be a globular cluster that we can't find or something like that. And so I think this is a really, really interesting avenue to try to find particularly very small dark subhalos. But one of the troubling things in light of this, subhalo disruption is, like I was saying before, we wouldn't expect very many subhalos within about 20 kiloparsecs. So on the left here is the number of subhalos that we would expect as a function of look-back time within about 20 kiloparsecs in the simulations that Tyler ran. And so what you can see is that for the dark matter only simulation, you would expect at 8 gig years ago, basically redshift 1 or 2, you would expect tens of subhalos to be around within 20 kiloparsecs that could potentially be perturbers to any globular cluster stream. But if you look at the disk simulations, there are far, far fewer objects, and at the present day, there's basically none. And so another way to look at this on the right, this is a plot from one of Shea, Garrison, Kimball's papers, where they, you can see this sort of subhalo radial distribution in the dark matter only plus disk simulation in that sort of fat dashed line. And then you can see on top of that, he's put shaded regions for where the Palomar 5 and GD1 streams are. And you can see that, at the present day, they're kind of just right at the edge of basically being able to perturb these globular cluster streams. And so there's many fewer subhalos than you would naively expect that could potentially act as perturbers to these globular cluster streams, at least very close into the Milky Way. There's obviously other globular cluster streams further out, and hopefully in the future, we'll be able to get better data for those and be able to identify gaps at a place where we expect many, many more subhalos. All right, and so as sort of a last thing that I wanted to talk about, sort of implications of this for what we could learn about high redshift star formation or kind of the smallest, faintest galaxies of the Milky Way. And so as a primer, we'll talk about a little bit about this old problem called the missing satellites problem, which is basically all the way back in 1999. Clifton et al. Sort of pointed out this potential issue where if you take sort of the subhalos of a Milky Way-like galaxy, which is sort of shown on the left, you would expect thousands, tens of thousands of these objects. But then if you look at the sort of galaxies that we know about that could fit into those halos, there are far, far fewer actual satellites than subhalos that we can fit those galaxies in. And the kind of canonical solution to this problem is that it's partially due to reionization. And so the idea is that reionization can heat up the gas around these halos, or maybe even penetrate a little bit into the halos themselves and heat up the gas within it, and either prevent accretion of gas or stop star formation in small halos. And in basically the very smallest subhalos, it should prevent the formation of stars entirely. So you'd expect below a certain mass, you wouldn't halo mass, you wouldn't get any galaxies at all. And once we started to get these hydrodynamic simulations, we actually saw this, and with modeling reionization, we actually saw this explicitly in the simulations. So this is from the Apostle simulations by Till Sawala. And this plot is the basically luminous fraction. So basically fraction of halos that host a galaxy as a function of halo mass that they saw in their simulations. And what you can see is that, around 30 kilometers per second in terms of Vmax, you start to basically decrease. You start to get galaxies that or halos that don't have a galaxy in them. And this matches with some back of the envelope calculations about how this might happen from the 90s, where around the reionization would start to impact these halos at around 30 kilometers per second. And then in these simulations, by about 10 to the 8, or maybe even 10 to the 9 in halo mass, you would actually expect all the subhalos to be completely dark. But what's interesting is there's this sort of middle region where you're not fully luminous, but you're not completely dark, where you would expect some halos to form galaxies, but those galaxies would be heavily affected by reionization. And of course, we know those galaxies. Those are the ultra-faint dwarfs of the Milky Way, which you can kind of barely see in this picture of one here. But more explicitly, you can look at the star formation history of one of these objects, for example, from Tom Brown's work. And what you can see is that there's most of these ultra-faint dwarf galaxies, when you look at their star formation histories, they're more or less consistent with forming all of their stars before reionization. And so this picture is kind of coming together. It looks really interesting. But there are some changes, I think, in both ways to this picture. So one is on the galaxy side, the sort of observed galaxy side. And one of the things that's happened over the past few years is an explosion in the number of observed galaxies. And so this is a plot from Josh Simon's recent review of ultra-faint galaxies. And what you can see is that, back when we only had photometric plates, we were discovering basically one satellite every decade, or one or two satellites every decade or so. But then when SDSS went online, there was this pretty big increase in the number of satellites that we found. That's from SDSS discovering ultra-faint dwarf galaxies. And then more recently, with the Dark Energy Survey, we've had a similar, even larger explosion in the number of dwarf galaxies that we found. And now today, the number is roughly 60 or so. And so we found a lot more galaxies than when the missing satellites problem was initially formulated. And similarly, to point this out again, we know that there are fewer subhalos than what was assumed in the early papers on the missing satellites problem, particularly very close in, where we would expect by basically many fewer or no subhalos at all. And so if you kind of revisit the missing satellites problem today, well, what we have is more galaxies and we have fewer halos. So what I wanted to do a couple of years back was investigate this in a little more detail in light of this sort of additional subhalo disruption. But sort of prime this, we kind of need to think about the sort of scales that we would expect different galaxies to fit into. So we're kind of doing a sort of light abundance matching, where we're looking at the sort of systems that should host galaxies and then how many of them there should be. So if we look at the sort of systems around 30 kilometers per second, that's where you would expect to be unaffected by reionization. And these are the classical satellites of the Milky Way. And then according to the plot on the left, there should be about 10 or so, which is exactly what we see. We see about 10 satellites that we call the classical satellites that didn't get disrupted by reionization. They formed stars basically until they were accreted by the Milky Way. And some are even still, like the Magellanic Clouds, still start forming today. Now we have the sort of known satellites, which lies around 60 or so. And if we sort of map that to this subhalo mass function, we would expect those objects to be at a mass of around 20 kilometers per second. So this is well within the regime where you would expect to be affected by reionization. This also makes sense because this is the ultrafaint. So most of the very recent dwarf galaxies that we found are ultrafaints, and they've been affected by reionization. But then there's this sort of ambiguous zone because we're not complete to the number of satellites. Our surveys are not complete. They're sort of surface brightness limited. And then also we can't really see things through the disk. So there's kind of the region of sky that's blocked off by the disk, but there could still be some satellites hiding. And studies have estimated that there could be between 100 or several hundred satellites within the virial radius of the Milky Way. So where exactly this point where we would, in terms of halo mass, where we would expect there to be a completely dark fraction of galaxies is kind of ambiguous currently. And so what I wanted to do was I wanted to take our subhalo distributions and sort of just paint on a toy model, basically just probabilistically draw from this distribution on the left, which is basically the dark fraction of galaxies or the probability a subhalo has to host a galaxy, and just take this function on the left and apply it to the radial distribution of satellites that we see on the right, and then compare that to the observed radial distribution of satellites, okay? And so I'm going to focus in on the inner 50 kiloparsecs around the Milky Way because we think that's roughly where we should be complete to ultrafaints. Outside of that, it's much, much more complicated because you have to deal with completeness corrections and all sorts of things like that. But we think that reasonably we should be complete to around 50 kiloparsecs to the ultrafaints. And so when we apply this sort of probabilistic framework to the subhalo distributions, we get this distribution on the right. So this is basically using this prediction for how reionization should suppress galaxy formation. We would expect the distribution on the right in blue for the number of galaxies that we would see within 50 kiloparsecs. And what you can see is that the median for this model is less than 1. So you'd expect less than 1 galaxy within 50 kiloparsecs, given this sort of fiducial picture of reionization. And the black curve is what we've observed with the SDSS and DES. And so we've observed about 11 or so, and we would expect from this simple model of reionization, less than 1. So this is maybe a little bit of an issue here. So then the question could be asked, well, what would we expect in order to sort of save this model? And so I added another toy model where I just sort of dropped the median of this function on the left to about 10 kilometers per second. Instead of what it was before, which is more like 20 kilometers per second. And in that case, you get more galaxies and smaller subhalos, and therefore you get something that looks much more reasonable. But it requires you form stars in much smaller subhalos than was kind of normally expected from this reionization killing galaxy formation picture. And it gets a little bit more interesting when you look at sort of the masses of these subhalos at high redshift and then calculate what the virial temperature of these halos would be. And so for these two models, the sort of fiducial reionization in blue and the sort of what we need to match the radial distribution of satellites in yellow, well, you notice that these two distributions actually kind of bisect the atomic cooling limit. So halos above this can cool via atomic cooling, but halos below this can only cool by molecular cooling or metal cooling, which is actually very interesting. So this is telling us that maybe this requires, in order to sort of match the galaxies that we're seeing around the Milky Way, it sort of requires you form in small halos that can only cool via molecular or metal cooling. And there's actually some evidence that that's happening. So these are some theoretical simulations from Munchie's work, particularly from the Chang'e simulate or the Chang'e code. And one of the suites of simulations, they basically ran a large suite of dwarf galaxies, and they ran one with metal cooling turned on. And what you can see is that on the left, they're able to form many of these basically stellar mass versus halo mass, and they get a bunch of galaxies that form these small metal cooling halos. Another interesting look at this was done by Ethan Nadler recently. And so he built this much more impressive and broader, basically machine learning framework to take into both like the data of observed galaxies and then what we know for the subhalo distributions, and then also the actual footprints of the surveys themselves. It's very cool work. And also sort of backed out one of the results of this was he backed out the fraction of luminous galaxies as a function of their peak mass. And so you get this fraction, basically galaxy fraction. And what you can see is that the sort of median, you see this decrease basically between 8 kilometers or 8 kilometers per second in Vmax and basically roughly 4, which is more or less what which is actually even more aggressive than what I sort of needed to match the distribution of galaxies seen around the Milky Way with just my sort of simple Tor models. The last point is one interesting insight into the physics that could be happening here is that, so like Massimo Riccati's work, they simulate population 3 star formation. And one interesting thing that they found was you can actually form ultrafaints in the sort of galaxies polluted by POP3 supernova. So what you have is a population 3 star forms, it then dies and explodes, and then that that material pollutes subhalos around it that are basically below the atomic cooling limit, but can still cool and form a galaxy because they've been polluted by these outside materials from this POP3 star formation. And so they're able to form these POP2 galaxies, which look roughly like ultrafaints in these very small dark matter halos that are smaller than you would typically expect galaxies to form. All right, and so that's more or less it. And I'll leave up my conclusions here, and I guess I'll take any questions.
Okay. Thanks, Andrew. That was a great talk. So does anyone have any questions before I ask any? You can. Okay, so I guess I was curious, like so how these works, I guess so is there too many satellite problem?
Yeah, I mean, I think in a sense, if you're sort of relying on this sort of canonical picture of how reionization suppresses galaxy formation, I think there kind of maybe potentially is a too many galaxies problem. But I think like through like, for example, Ethan's work, Ethan Nadler's work that I showed before, he's sort of able to build in the statistical framework, and sort of the only additional point that you need to add is you just need to assume star formation is happening in smaller halos. So I don't think it's like a crisis for cosmology. It's just sort of, there's this additional picture of where galaxies should be forming, or the types of halos that galaxies should be forming in, that already kind of matches, like I was showing, already kind of matches what people who work on very high redshift star formation are also finding. So it's kind of bringing those two fields together in a really interesting way.
So yeah, so is it just about galaxies and not like halos themselves? As in, is there if you're finding all these dark subhalos with like gaps or lensing, or substructure lensing, I mean, so I guess if there are too many like dark matter halos, that necessarily wouldn't be solved by reionization, right? Or is that just not the case, that there's the exact CDM amount of halos?
I think at least as far as the Milky Way is concerned, because we don't have a complete census of the dwarf satellites, I don't think we can say that there would be too many halos before we would say that, okay, we're just not able to detect all the galaxies yet, because we know we haven't seen all the galaxies. And even, we're seeing incredibly diffuse, like Antlia 1 is an incredibly diffuse galaxy that was more diffuse than we were expecting to find. So there could be many of those that would even throw off, presumably, these predictions that I've been showing. So it could be also that there's just these very faint diffuse objects as well.
So do you expect JWST to like have another sharp uptick of?
I'm not. Yeah, I think I would hope so. I'm hoping so. If not, certainly, yeah, further on with other surveys. I think, yeah, like the Vera Rubin telescope with the that's hopefully the next one, and we'll probably be able to see. I forget what the projections are, but I want to say we should be able to see stuff out to the virial radius, like ultrafaints out to the virial radius, which would be very exciting.
Cool, cool. I see that Christoph has a question.
Yes, what's the dark matter fraction in the tidally stripped galaxies? And would you expect the dark matter fraction to be observationally overestimated because the baryonic component is kind of stretched, and if you do velocity dispersion measurements and you're a little bit biased by your line of sight?
Yeah, so I think one of the things about, so there have been studies from others, I'm trying to remember, I think Azi Fatahi did some work on this, where they were looking at, she was looking at hydrodynamic simulations, what is actually happening to these halos as they're stripped. And what you see is that a lot more, you have to strip out a bunch of the dark matter mass, like basically 99% of the dark matter mass, before you actually start affecting the galaxy itself. It's actually a shocking amount of how much mass you need to strip out. So I think typically, in these, when we're looking at the observed galaxies, we're expecting them to be dominated by dark matter. So like dark matter fractions, like 100 times more dark matter mass than baryons, or even 1,000. But that doesn't even necessarily have to be the case. And we wouldn't necessarily be able to tell that dynamically, because you have to strip out so much of the dark matter before you actually start affecting the stellar distribution.
Okay, thank you.
Yeah.
Okay. Any last questions? So maybe saying none at the moment. I guess we should all thank Andrew again for giving a great talk. This was the last one of our current semester of the CosKASI ECR seminar, but we'll restart again September 2nd with Ulrich Kushner from University of Nottingham. So please come back then. And